How do scientists investigate polar subglacial geology? Imagine trying to understand what lies beneath a thick layer of ice that smells thick. That's exactly what scientists face when they want to learn about the geology under polar ice sheets. They use a mix of advanced tools and techniques to peek beneath the ice without actually drilling through it all the way down. One of the main methods is airborne geophysical surveys. Scientists fly specially equipped aircraft over the ice sheets, using sensors that can see through the ice. These sensors include high-frequency radar systems that send radio waves at 150 MHz to penetrate the ice and reveal the bedrock below. They can measure ice thickness, internal ice layers, and even find hidden lakes trapped beneath the ice. These aircraft also carry magnetometers that detect magnetic signals from the crust below, helping map the structure of the bedrock. Gravity meters are used to measure variations in gravity caused by different types of rocks and sediments underneath the ice. These flights have covered key regions like the Amundsen Sea embayment and Wilkes Subglacial Basin, giving scientists a clearer picture of what's hidden beneath the ice. Satellites are another vital tool. They use laser pulses to measure tiny changes in the ice surface. When a subglacial lake fills up with water, the ice above bulges slightly, and satellites detect this movement. When the lake drains, the surface dips down. This helps scientists track water movement and understand how subglacial lakes fill and empty over time. They also use radar technology called differential interferometric synthetic aperture radar to monitor how water flows beneath the ice on a daily or weekly basis. Seismic surveys add another layer of detail. Scientists set off controlled explosions or use special sensors to send sound waves into the ice. These waves bounce back from the bedrock and layers beneath, revealing what kind of materials are down there. For example, seismic data has shown that beneath fast-moving ice streams, there's a layer of glacial, a mix of mud, sand, and pulverized rock that helps the ice slide more easily. Ground-penetrating radar is also used near ice shelf grounding lines to spot subglacial lakes and channels where meltwater drains into the ocean. When it comes to direct sampling, scientists have developed tools like the Recoverable Autonomous Sonde, or RECAS. This device melts its way through the ice using a special thermal drill called a Filbert probe. As it melts, the water refreezes behind it, allowing the sonde to reach the base of the ice sheet. Once there, it collects water samples and measures temperature, pressure, pH, and conductivity. It then returns to the surface with its data, all at a fraction of the cost of traditional hot water drilling. When boreholes are drilled deep enough, scientists can extract ice cores that contain tiny mineral particles from the bedrock below. Analyzing these mineral inclusions with microscopes and other instruments reveals what kind of rocks are beneath the ice, like quartz, feldspar, or apatite. This helps piece together the geological history of the area. The Polar Observing Network, or POLNET, uses GPS and seismometers installed on exposed bedrock to monitor how the crust moves as ice melts or shifts. These measurements help scientists understand past glacial movements and predict future changes. Combining all these methods gives researchers a detailed picture of what's happening beneath the ice. They can create three-dimensional models of the subglacial landscape, track water flow, and understand how the geology influences ice movement and melting. This integrated approach is key to understanding how polar regions respond to climate change and how their hidden geological systems work.